continue our, we have now integrals, right? So before we continue on integral, um, is there any specific question about the midterm? Like, um, I think your TA already gave the answers, right? Or discuss the answers. I will give you the notes for the answer key, okay, later. But do you have any specific questions for from this question? I think most of you are for number 16. Okay, you need to sketch the curve, right? Most of you didn't sketch the slant asymptote. The slant asymptote. So the asymptote is not horizontal or vertical. It's also having the line equation. If you divide uh, this 3x squared minus x plus 2 divided by x minus 2, it should have, if you divide directly, it should have a line equation, right? So it should have a line equation plus some fractions here. That line equation is the slant asymptote, and it will define your the curve. Okay, so the curve should be like so the curve should be like this. The curve should be like this. So you have a slant asymptote, the green one, and then there is no inflection point. Okay, there is no inflection point, even though this is concave downwards, this is upwards, because we don't have any f double prime equals 0. Still, it's not having inflection point, but you can find the downwards and upwards. Okay. Suggestion for you. Okay. So if you are having a functions, big functions like this, okay, 3x squared minus x plus 2 over x minus 2. It's really, really useful if you can make up these terms. It's much more easier to derive, right? The same thing in integrals. Whenever you have integrations, like big fractions like that, it's easy to integrate each of this, right? Rather than this big function, okay? So that is one suggestion for you. So from here, this 3x plus 5 is the another asymptote, okay? Um, finding this f prime and then the f double prime. So from the f prime, going f double prime, it's much more easier, okay? Rather than having the quotient rule, f prime g minus g prime f over g squared, and then you will have long terms, okay? And you can simplify, and then you get the f double prime. And notice that there is no inflection point, okay? No inflection point, but you still can use this vertical asymptote to check the concavity. Okay, that's number 16. Okay, any other specific questions related to midterm? If there is no, I will send you the PDF later. Okay, you can review if you want. Because, okay, even though we will learn integral, some of fundamental concept from the derivative still, you can still use it in integrals. Okay? Because I think in another sections, you will learn the relations between the first or the derivative and integration. Okay. Okay. If there's no questions, we can move on to last discussions. We have the definite integral. Okay. That's the one thing that you need to at least pay attention is this form. Okay. This form is the basic definitions of integration. Okay. So you will have integral notations. Oh, by the way, how many of you didn't study integral in high school? 1, 2, 3, 4, 5, 6, 6. Okay, 6. Okay. So the best way to define the integrations, okay? The best way, first, based on intuition. Based on intuitions means if you have, for example, okay? For example, if you have this is x squared, okay? You can derive, okay? The integrals is when you have 2x dx, it brings back to x squared, okay? And from here, we kind of make a building blocks for integrations. That is, for polynomials, we have for x, so for f is x with the power of n. Then if you have integrations, then you will have n plus 1, x n plus 1, and you need to add plus c. I will explain more for the constant, okay? But for now, let's treat the integrations as the reverse of derivative. Okay? So if you know something to some functions and some derivative of that function, then you can reverse and make the original function. And that is the way integrations work, right? The other way is instead of looking the reverse, the backwards, okay? Instead of reverse, we can also think the integration as if you have integrations from specific number to specific number, let's say a to b, okay, fx dx, okay. So fx is if you have functions, then this is your fx, okay. It's the height, okay, of the if you have building blocks like this height is fx, right? It should be delta, but let's say we approach delta to become dx. Okay, so the fx dx, if we put all building blocks and we plus or we add 1, 2, and more until infinite number and approaching infinity, then we can actually approach the integration with geometry. Okay, with geometry. We can approach with geometry, which is the area under the curve. Okay. So we have in your textbook, we have chapter 5, 6, 7 for integrals. Okay. So 5 will be the definite integral, the Riemann sum, and some techniques for integration. Okay. Chapter 6 is looking at the area under the curve, between curves, and the volume. Okay, so if you have the area here, imagine in your brain, okay, imagine you are rotating the area, and it will become like a, for example, if you have just like this, if you rotate, maybe it will be like uh like this, right? Maybe you can put a flower here. Right? Yeah, it can be a solid volume. Okay, it can be a volume, and that is the chapter 6. And chapter 7 will be another techniques for integrations. Uh, we call the integration by parts, but I think some of you already know. But I will give you another techniques that I think it's not really well written in your textbook. Okay? But later I will show you. Okay. Now, I think I can give you some I can give you some intro. Um, or maybe some property in integrations. Okay. So if you have integrations, let's say we have 0, 3. Let's start with the easy one. What I want to show is uh, you can integrate this easy, right? Very easy. You can have 1/4 x4, right? And 3 x squared, right? And you can plug in 0 and 3, right? You can get easily by using our intuition that the integration is the reverse of derivative, okay? The backwards of derivative. But actually, if we are looking at this whole sigma, or here, this sigma fx delta, okay? If you want to calculate these integrations using the basic definitions, okay? Meaning we need to change these integrations into sigma, into sum, okay? Let me tell you how. So by definitions, let me write the definitions. Okay. Let me write the functions first. The functions is x and minus x. Okay. And the interval, the AB interval is 0 and 3, right? And then we need to find the delta x. The delta x will be 3 over n. Okay? It's not specifically uh, given the n. Okay. Uh, I think you can also try using the Riemann sum if you want. Try maybe left endpoint or right endpoint or maybe midpoint, trapezoidal, and maybe you can just use any n you want. Maybe 8, 9, 10, okay, and compare the results with the true results, okay? Because the Riemann sum is only approximation. Okay? But let's see here, okay? Our delta is 3 over n, okay? Our f, our xi, meaning the sample point, is 3i over n, okay? Then our equations will be f 3i over n, 3 over n, okay? And use this 3i over n to the functions. In derivative, it's similar to limit h0 x plus h minus x over h. Remember that? Okay. This is somewhat similar to that. Okay, somewhat similar. But here we are using the sigma. And then, oh, let me factorize the 3 over n. Okay, so basically, we are using the 3i over n as our sample point, put inside the x cubed minus 6x. and we get this expression. Let's solve this. Okay, we get these expressions. Let's multiply all with 3 over n. Uh, okay, now from here, we get I cubed and I. Okay, we can use some formula here. For I is n plus 1 over 2. For I cube is n plus 1 over 2, and then squared. Okay. This sum formula, some of them easy to prove, some of them having long for proving. There's a lot, but if you are facing these questions, you can always look up the notes, and if it is happening in your exam, I will give this to you. Okay, so don't worry. So we change all the I into the formula for n. So basically, it's the, if you remember your, maybe in high school, you have the series, right? Like 1 plus 2 plus 3 plus 4, blah, 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 right? And you have the formula for the series. So let's change all into so this will be n plus 1, and then divide by 2 squared, and then this become n plus 1 over 2. Okay. Let me make this smaller. So limit and approaching infinity. It will be, I will move 4 outside, and will be 1 plus 1 over n squared. And then this one is 27, and 1 plus 1 over n. Yeah, I think that's correct. Okay, now this 1 over n, let's substitute the limit inside the n. Okay. Substitute the limit, this becomes 0, 0. So the solution is just 81 over 4 minus 27, which is, it's around 6, right? Or 6.5. You can try with calculator. If you bring calculator, you can try integrations using the functions, okay? Using these functions, and integrate from 0 to 3. What is the result? Can you calculate? You check x cubed minus 6x. X cubed. It is this. Yeah. And then you put x. Uh, here, x cubed. Okay, anyone? Another calculator? Bring calculator? No? Yeah. Yeah, and this is negative. Okay. 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 So our calculation is correct. So based on what we have done here, basically this is integrations using the basic definition, okay? Using the limit definition of sum. Okay, and still you can do it. Okay, but for more complex one, we will have another techniques. Okay, although this is true for every integration that is integralable. Okay, every function that can be integrals, you can do this way. But sometimes it's very long and really hard. Okay, but at least this is showing you the we can use it to calculate the integration. Okay, and another note for I think for Riemann sum, uh, what you are doing in Riemann sum basically just calculating the geometry. Okay, if you are knowing the approximations, how many rectangles you have, and maybe what error you want to have, and you can just type in the numbers and calculate. Okay. Okay. Um, any questions? Okay. I think this is just showing you how to integrate with um, basic definitions. But later, for if we have another techniques and we know some of integrations by default, you can just integral using integrals any way you want, as long as it is correct. Okay? This is just a basic primary definition. Okay, I will move to sum property. Okay, sum property in integrations. I think the property will be somewhat a little bit similar to derivative. So for definite integral, you will have the basic property, and then you have if you have constant, if you have plus integration functions plus functions plus or minus, you can separate A, B, also minus. If you have A, B, constant, fx dx, then you can move out the constant. And then you can also have okay. So if you can also separate, if you have C in between A, B, you can separate the integration. Okay. Okay, I think not really um, a problem. Now, maybe you can take a look for a while. Okay. I think similar with derivative, right? Somewhat a little bit similar. Okay. The next one is uh, we call its comparison property. So if okay, you have functions greater or equal 0, and you have A and B as your interval, so your integrations of functions will be greater 0. And if you have functions greater than another functions, same interval, and you have these conclusions. Okay. And third one, let's say you have m small equal functions, and it's also less or equal the capital M, same A and B. We can write, because M and the big M is a constant. So if we have integrations of A, B, fx dx, then this will be M B minus A, right? And this M also B minus A, like that. Okay. And maybe we can also uh, draw the illustrations. Okay, let's say this is the big M, this is the small m. Let's say it will touch the, okay, let's say that's the functions. And let's say we have A here and B here. And we can say that if you remember the chapter 4, the maximum minimum, right? So if you have only this interval, so this is maximum value, this is minimum value, right? We will get back into the graph, this graph later, but I will tell you another sections first, and then I need to prove some theorem. This is called the fundamental theory of calculus. So if we have functions continuous on a, b, let's say that is our functions. This is a, this is b, this is functions. Okay. Let's say we have in the middle, in between a and b, we have some numbers. Let's say we have x here. So area under the curve from a to x. Okay. Let's say we have f x is equal a to x. Okay. Okay. Now this is x. Now the functions will be f, usually fx dx, right? To avoid that, because we're also using x, I will use another variable, which is t. Okay, I will prove why this is correct. Okay? So let's write first. This is ft dt. Okay, the f means this is the antiderivative of the small f. Okay, and x is on the interval a, b, and the big F is continue and differentiable. Differentiable on a, b. Okay. Okay, you still remember why I have interval, closed interval, open interval? Okay, please remember why this difference. Okay. Okay, so I need to make this blue color assumptions to make the this statement true. Okay, so this is true if the big functions f is continue, differentiable. Okay, and if it is true, then let me write. If that is true, then if I differentiate, okay, if I differentiate the big F, okay, which means I'm finding the first derivative of these integrations. Okay, the conclusions is okay. The conclusion is just f of x. Okay. Every continuous small function f has antiderivative the big F. Okay, this is called the fundamental theory of calculus. So this is the sections where we need to relate or we need to connect, okay, the idea of derivative and the idea of integration. Okay, I will make some writing some proof why this is true. Okay, it's quite long, but I think you can just point out the key points. Okay. Also, this is the second. Okay, second, based on the fundamental theory of calculus, if f continues on the interval AB, if you have definite integral, then it will be where f is antiderivative. Okay, so actually, okay, I will have a conclusion first, and then I will prove. What this theory tells us is, if you want to make this 2x integration become x squared, okay, if there is no theorem about that, then this is, you can't do this. You cannot do this. But, okay, because we already make some theory here that states if you find any reverse derivative, any antiderivative, okay, if you have that form, then you can use that form and plug in the number and minus, and then you get the results, like you did in the x cubed and minus 6x, right? The x cubed minus 6x, okay? If you want to integrate this, okay, let's say the x, we can easily say we have, okay, x4 and then divided by 2, 3x squared, right? We can say, okay, this is our antiderivative, okay? And because we have this theory, that's why we can directly integrate this into this and then plug in the number b and a, and then we get easily the answers, okay? So that is why, okay? That is why. If there is no theorem like the antiderivative theorem, what you can do is using the sigma. That's the integrations by definition. Okay? But we have this theory, and it will make your integrations easier. Okay? If you find any antiderivative form, for example, okay, you have functions is tangent x. I think if you have f prime is what, secant squared, right? Secant squared x, right? And if you have, for example, secant squared x dx, because you know these two forms, okay? You know the relation between these two. Then we can apply, just make it tangent x plus c. So integration and derivative, we cannot separate that two. Okay, we cannot separate the two. And sometimes the idea from derivative is really helpful for integration. Okay. Okay. Now I'm going to proving this theorem. A little bit long and boring, but I hope you can keep it, at least the key points. Okay. Okay. Suppose. Oh, let me write this is to proving. So proving. So suppose functions is continuous on AB. A x is in between. So if the big F then f prime x is fx, and f is continuous on AB, differentiable on AB. Okay, this is just the first statement. Actually, the proving is the second one. So let me write first, okay, if x and x plus h. Okay, let's say we have x and x plus h. This both on interval AB. Okay. Okay, let me write the x and x plus h. Okay. So x and x plus h, let's make these two become our point of integrations. So we are using this form and changing x with x plus h, okay, and x. So we are evaluating both x plus h and x. Now, this form here, these integrations we can separate because this x plus h and x is the same thing in derivative with limit. So we have x and then plus h become x plus h. So the distance is h, right? So I can make this become n plus x, x plus h, ft dt, and minus the a x ft dt. Okay, this part is canceling. Okay, so basically it's telling us that we only consider the integration from x to x plus h, which is actually in our assumption is correct. Okay, which in our assumption is correct. And then let's make some notes. Okay, notes for h is not 0. Let's divide all with h. And assume h positive, okay, and f continue on the x and x plus h. Okay. Now from all the calculations before, now we consider we only have two endpoints, x and x plus h. Okay. Let me write first, and then let me point out which one is the essential. Okay. In extreme value theorem, or in Rolle's theorem in chapter 4, suppose, okay, there are u and v on x and x plus h, where the fu is m and fv is the big M. Okay, and we call this is minimum value, and this is maximum value, as we can see from previous slides. Okay, the small m, the big M. Okay, let me draw the illustrations for you. It's a bit different, but I hope you still understand. So this is M, this is small m, and this is U, this is V. Okay. So M is our minimum value, and the big M is maximum value. Our functions is in between those two values. Okay. If we can integrate this with AB, then we get this is B minus A. This is B minus A, right? The comparison theorem from previous. Okay. And similarly, okay, remember we have the ft x and x plus h. Okay, let's make the distance between a and b become h. Okay, so let's make this and this become x plus h ft dt. So we have these terms divide all by 1 over h. And turns back the m into our functions. And these integrations, okay, the middle one, let's turn into our f x plus h minus fx divided by h. And you see what we are doing right now? Familiar with this form? From the, if you get limit, 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 you get the squeeze theorem, right? This limit in the middle is derivative, okay? So basically what we are doing is we need to proving the integrations, the ft and let's take out some information and making these integrations become definition for derivative. Okay. Okay, we get this point now. Okay, now in limit, you probably familiar with as h getting closer to 0. Okay. What's happened for u? Remember, if this is x plus h, then u will be getting closer to x, right? And the same thing for v is also getting closer to x. Okay. U and v is any number in between x and x plus h. Okay. So if there is no h, then u and v will getting closer, both u and v getting close to x. Okay. And then because of that, then limit as h getting 0 for fu, I can write this limit u to x of fu, which is this is the fx. Okay. And the same thing for fv. this is also getting close to x, and our function is the same. And by Squeeze theorem, okay, in limit, then limit of h getting 0 of fx plus h minus fx or h is fx. So these integrations, or let me write this f prime. This is f prime, right? F prime x is fx. Or we can say that d dx of ax ft dt is true. This is going to become fx. So what does this actually means? If, okay, let me write in the simple words. Okay, if we first integrate f and differentiate the results, we get back the original f. Okay, so you integrate, differentiate, basically this ddx. If you have any ddx as your differentiation, and you are putting this differentiation before the integrations, meaning you are canceling this too. And the answer will be the original function f, okay, which means f in x. Okay. Okay, there's another proof actually, but I think I will skip that and maybe just making notes for you. It is this, if you have this fxdx, there's actually some proving for this one, but I think I can just make some notes. It's not really long, but this is important point for integrations. Okay. Any questions first? Any questions first? Let let you think first, or maybe let me. Okay. Let me um, slowly explain to you. Okay. So if all functions continuous, differentiable, blah 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 on the interval AB, if you have x and x plus h inside the interval AB, okay, if we analyze this big F, the antiderivative, x plus h minus fx, okay? And if we assume with f t dt, okay, first we get these expressions, and we can simplify the expressions, just become x and x plus h, okay? Meaning, if you have point, 1 point and second point, first point and second point, you can use that easily on integrations, okay? And let's divide this by h, okay? And this also 1 over h here, okay? Let the h become the definition from x and x plus h, the distance in between those two. And we assume h is not 0, and also it's positive, okay? It's continuous on and x plus h, okay? And we get these expressions, and then looking the extreme value theorem, it's in chapter 4 actually. It's the Rolle's theorem. There will be max and minimum value on the continuous function. Okay, yeah. So if we have, let's say, just make other variables u and v on x and x plus h. If we have this maximum value and minimum value, okay, we can use the comparison theorem from previous slides. You use this theorem. Okay. Use this theorem and then exchange the b minus a with h. Okay. So mh and the big mh. Okay. And divide all by h. So multiply 1 over h. So we get the minimum value is less equal 1 over h integral from x to x plus h f dt, and less equal the big M. Our M and big M, as we mentioned before, is our max and min value from our functions f, small f. And we put back our functions of u, functions of v, okay? And then what we are doing now, we are using the limit. Okay? We are using the limit, okay? So as the h approaching 0, because u and v is on x and x plus h. Okay? If h is becoming 0, then u will be closer to x because h is getting 0. Okay? And v will be also closer to x. Okay? And both fu and fv, if you are limiting the h to 0, u to x, then it's just the fx. Both functions become just fx. Okay. And by the Squeeze theorem, because the first and the last part is fx, then limit as h equal approaching 0 is also fx. And this part, based on our definitions in derivative, is f, the big F prime, right? So this is to conclude, to prove that, okay, it's true that the big F prime of x is our function, the original function. Okay. Yeah, that's to prove that is correct. And we can also say that if you have any ddx and you have integrations, basically these two will be canceling, and it will return the original function of this, which is the fx. I hope you still not confusing the variable t here. Okay, this variable t is another variable to make these integrations make sense. Okay, because this is x. Why this is x? Because we want to approach some number to x. So if we are differentiating the integral, we are getting only fx, and this a will be gone. Okay. 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 So this is a key point. Okay, in this section, the fundamental theory of calculus. And second is this. Okay, for definite integral. Second is this. So if you have integration a b, basically you can minus the antiderivative, the fb minus fa. Okay. So basically, that is the fundamental theory of calculus, and this is the definite integrals. Okay, we'll make notes. This is definite integral. Okay, now I will move on to indefinite integral. Okay. So the idea for indefinite integral is you are having only this, okay, only fx dx. Okay, there is no specific uh, number. Okay, for the endpoint, there is no specific or exact value there. So this is usually usually used for common antiderivative. And it's called the indefinite integral. This is just from previous slide, so it's writing to begin the indefinite integral. Okay. So in indefinite integral, to find this antiderivative, the big F, okay, we need to make some property and some. So if you remember any differentials, derivative, okay, for example, this tangent becomes secant squared, so the integral of secant squared is tangent, and maybe from here also, if you have x with the power of n, you will get this, okay. Several derivative like sine, cos, the inverse tangent. You can forward and backward make the relations between them, and you can find the integrals. Okay, but okay, um, if you have, for example, let's say fx is tangent x to the 4. Okay, and based on our first derivative, it should be secant squared, right? So let me write the f prime, and it should be secant squared x4, and then don't forget to multiply with 4x cubed. Okay, this is the first derivative. Now, um, let me write the chain rule. Okay, just to make sure the notes. So if you have integral secant squared, or let me write 4x cubed secant squared x4 dx. if I have these integrations, okay, what will you write here? I already make my original function is tangent x to the 4. F prime is secant squared x to the 4 and 4x cubed, right? So if I integrate this, actually you will get these results, right? But what will happen if this is not given? If this is not in the information, not given, what will you do? In derivative, you can do easily by applying the chain rule, right? So what we will do to integrate this, also applying the chain rule, but reverse, okay? But reverse. To make it reverse, then we can start with, if you have the chain rule, you see the x4, right? And you have 4x cubed. Okay? This 4x cubed is the result of this, right? So let me write here. So ddx of x4 is 4x cubed. Okay. So if I substitute the x4 with something maybe u, okay, let x4 is u, then du is 4x cubed dx. Okay, see here, 4x cubed dx. Now, if you want to change this form, we have x, 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 right? Let's change this x, x, x into u. So x4 is u, so this is become u, okay? And du is 4x cubed dx. So dx is du over 4x cubed. Let's put dx here. Let's put dx, and then this 4x cubed will cancel, right? Okay. So secant squared u, and then dx will be, let me write, okay. So because this canceling, then we get the secant squared u du, right? And this is just tangent u, right? Let me write tangent u first. But because u is x to the 4, and I want to make the original x, let me change the u into x to the 4. And don't forget, we plus the constant. My 4 is similar to u. So let me, okay. Okay. Remember, okay, this is just my suggestions, okay? Whenever you have any u here, sometimes you are get used to plus c here. Okay? This c, when you change the u back to x4, the c will be different. My suggestions, always plus c at the very end. This part is okay, you still have u, but when you make the final equations, you can write plus c. Okay. So this is called the U-substitution, or just substitution still fine, because you can make this u, v, z, any variables you want. The idea is just substituting as a means for the chain rule, okay? For the chain rule. So if you want to look at where's the chain rule, is from okay, from here. Okay, so that's why we are using the u as a gap between the functions and the x. Okay. But actually, the techniques in practical, it's not really that difficult. It's not that difficult. Let me give you examples. Okay, examples. Okay, let's start from the not that complicated. Let's start from x cubed, x to the 4 plus 2 with the power of 5. Now the idea, okay, because in these techniques, you should choose which part you want to be substitute with u. Okay. I think it's not that difficult because you have the first one is x cubed, the second one is x4, right? So you see x4, if you differentiate, become 4x cubed. And maybe in the calculation, the x cubed will cancel. So let's say we are making this whole thing x4 plus 2 become u. Okay. So let the u equal x to the 4 plus 2. And we differentiate for x cubed dx. So your integrations will be, you have 1 over 4. Let's say this x cubed, and it's canceling. And then you have u5 du, right? And it will be 1 over this 5 plus 1 is 6. And it should be 1 over 6. 6, 4 become 24. Okay. And let me write this as x4 plus 2, 6 plus c. And this the final answer. Okay. So the idea is how we choose our u, okay, to substitute the elements of the function. Okay. Okay, before we going for some examples in use substitutions, okay, I'm going to tell you another method besides the use sub, and next is integration by parts, but I will go the integration by parts later after chapter 6. But I will tell you the idea. Okay. Okay. Let me give you examples. Okay. So based on our U sub, okay, based on our U sub, you can see the 1 plus x squared. If you derive, it becomes 2x, right? 2x and x will cancel. So if you are using U sub, you can also get the results. Okay, let me write the U substitutions. So it will be 1 over 2, and then it's become u negative half du. Okay, and then you can directly find the integration. Easy, right? Okay. Another way to look at these functions. Okay. Okay. See here. If you have f of x is square root of x. Okay. If this is your functions. Okay. What is f prime? 1 over 2, right? Okay. Agree? It's true, okay? What if this is plus 1? It's also plus 1, right? Okay. Okay. Now think this function. It has the same similar structures. So if we can think forward and backwards, we can think some functions that when we differentiate, it will become this. What is function before this? Okay, got the idea? Got the idea? So if we have 1 plus x squared, if this is our functions, then the f prime is 1 over 2, and then multiply with the chain rule, right? And then, okay, then this is your answer, plus c. Okay, this is called the advanced guessing. And sometimes it's more powerful than the U-sub or integration by parts. If you have learned the U-sub before or the integration by parts, you know that integration by parts, most of the case works with any function, most of the case. But it's still long. It's still long writing. But here, if you can guess some functions that you can relate to, you can get the answer easily. So let me try another function. So if you have e to the 6x dx, what is the result, the integration? I think e is not too difficult, right? If you have e derived, it's still e, right? E to the x, derive e to the x, right? E to the 2x, it will be 2e 2x, okay? So if you have e 2x, it will be 2 and then e 2x, right? If you have e 6x, okay, it becomes 6, right? 6. Okay. So the integrations 1 over 6. Okay. Okay. And this makes sense. Okay. Uh, you can use this method in your exam. Okay. Um, maybe try one more. Try one more. for the e to the 6x, I think that's not too difficult. The function is not really difficult. You can directly get the answer. But for some maybe little complicated functions, you can write down any guess you want. Maybe you can write let functions maybe become this, and you try to derive first and try to make some conclusions, and then you can write down your answers, okay, to simplify the solutions. You can use u sub if you want, like this x squared is u, and then u it's become 2x, and it will be half, right? But you can also try to guess. Okay, guess. Uh, let's try to derive this. It will be negative 2x and e, right? It's make the same form, except it has negative 2. So the answer will be negative half e to the negative x squared plus c. Okay. Somewhat this is really faster. And for some complicated functions, this also can be applied. Okay. But I think not all, but mostly if it can be applied, it will be much more faster than u sub. Okay. Now let's keep the advanced guessing for a while. Okay. I will tell you a little bit about the constants, why we are having these constants and why it's important. Okay. Okay, try this one. Sine x cos x dx. Okay, what's the answer? Okay, what's your answer? Sine squared x over 2 plus c. Belum bisa nggak? Hah? Pakai substitusi bisa nggak? Bisa nggak? What's your answer? Yeah, you can use it. Okay. What's your answer? Okay. So you half sine squared x plus c. Okay. Let me write that. What is yours? negative half. Okay, which one is correct? Both, right? Which one is correct? Which one is correct? I'm not saying only one is correct, but both correct, right? So it seems different, right? But when you derive, the sine squared x become 2 sine x cos x, right? And it's just sine x cos x. This one, derive, it's cos sine x and negative will be canceled. The same, sine x cos x, right? The problem is here. Okay, this is to prove that this is actually C1 and C2, different constants. Okay, if you're trying to subtract this both functions, okay, let's subtract half sine squared minus half cos squared. It's half, right? Sine squared plus cos squared is 1, so it's half. So half plus C1 plus C2. So C1, so C1 and C2, if this is equal 0, is actually the gap between the constant is half. So the constant is different value. It's having different value. So that's why in every integration, you need to write the C. Okay, you need to write the C because the constant will make difference. Will make a difference. Okay. Okay. I'll have several questions for you. For exercise the U-sub. Okay. I will write the so number 1. Or let me make small. Okay. This okay, the second one is secant squared x and tangent squared x. And number 2, integration sine x. Yeah, from 0 to pi over 2 sine x over 1 plus cos x. Sine x and 1 plus cos squared x. Yeah, at least there's 3 questions first. There's 6 questions, but I want to see. Okay, so I would just want to show in general, mostly integrations is a little bit harder than derivative because you are imagine some functions before the functions being differentiating, okay? And you need some techniques to reverse how the derivative process is, okay? And see that if you just sin x over 1 plus cos x, maybe it's easy, but when you make square here, maybe that will be different story. Like this x squared, and you're having x minus 1. From here, it's much more easy like we did before. X squared, you can derive 2x, right? You can cancel, but what about this one? You need to think how to find it, okay? I will explain all next Thursday for this U-sub, and also several property for integrations. And if we can finish faster, then maybe I'm going to have the area between curves, okay? Because it's not that different from what we have done in area under curve, okay? The area between curve is you have 2 curves, and then you need to find the area between them. Okay, I think I will stop for today and see if you can find the solution. Okay. Any questions? Do you have any questions? Oh yeah, and next Thursday I will give your midterm. Okay.